In the last class, we have discussed about the centroids and centroid function, objective functions we have discussed, right? Okay, today we'll discuss the K-means additional issues and strength and weakness at the end. This K-means algorithms, additional issues we'll discuss, okay? So this is one of the issue, handling empty clusters. One of the problems with the basic K-means algorithm given earlier is that empty clusters can be obtained if no points are allocated to a cluster during the assignment step. So we have an assignment step, right? So initially we assign some points to some cluster. So while in that assignment step, if no points are assigned to a cluster, means that cluster becomes empty and it will create the empty cluster also. If this happens, then a strategy is needed to choose a replacement centroid. Otherwise, the squared error will be larger than necessary. So since cluster creates with empty points, that is no points, with no points, so squared error will be larger. Okay, squared error will be larger because it will not contain any points only for while calculating the squared error. Okay, so we need to choose a replacement centroid. We need to select other centroid. We need to select other centroid so that all the points will be assigned to some cluster and no empty clusters are created. Okay. Next issue, it is outliers. When the squared error criterion is used, outliers can influence the cluster that are found. Okay, outliers means the points which are not interested, the points in which the user is not interested. For example, if you are clustering using some image, and in that image, if it contains some objects, for example animals, you are interested only in the animals, not other objects. Okay, so other objects can be considered as outliers here. Okay, only animals are the object that or the points that you are interested in. Okay, when the squared error criterion is used, outliers can influence the cluster that are found. So outliers might influence, that also might be included in the cluster which we are going to find. When the outliers are present, the resulting cluster centroids or prototypes, usually centroids are also called as prototypes, right, may not be as representative as they would be, and the SSC will be higher as well. Okay, so if the outliers are present, the cluster centroids, the cluster centroid will be not as it is. Okay, it will be in the different place. It will be in the different place, and sum of squared error will be also more higher. If we use approaches that remove outliers before clustering, we avoid clustering points that will not cluster well. Okay, so we can use the approaches that will remove the outliers before performing the clustering. Okay, but it may remove the clustering points. It may remove the clustering points also with that outliers, and it will not cluster properly. Okay, so alternatively, what we can do, outliers can also be identified in the post-processing step. That is, after performing the clustering, we can find the outliers. Okay, for example, if we can keep track of the sum of squared error contributed by each point, for each point, we have to calculate the sum of the squared error and eliminate those points with usually high contribution to SSC. Okay, so we have to eliminate the points which are making this SSC more. Okay, which are making this SSC higher. Okay, and this can be done over multiple runs. If you execute more number of times, you will come to know which points is contributing to increase the value of SSC. Okay, those points can be removed. Next issue is reducing the SSC with post-processing. Way to reduce the SSC is to find more clusters, that is to use a larger queue. Okay, number of clusters, if you increase the number of clusters, for example, instead of creating 3 clusters, create 6 clusters. Okay, this is one way to reduce the sum of squared errors. In many cases, we would like to improve the SSC, but don't want to increase the number of clusters. Sum of squared error we have to decrease. We want to decrease the sum of squared error, but we don't want to increase the number of clusters. In that case, This is often possible because K-means typically converges to a local minimum. We know that it will converge to a local minimum. It will not create the exact centroid. It will not give you the exact centroid, but it will converge to a local minimum. Various techniques can be used to fix this. Okay, various techniques we can use to fix this. That is when we want to improve the SSE. Improving the SSE means reducing the value of sum of squared error. Okay, we want to decrease the sum of squared error, and we don't want to increase the number of clusters. For that, we can use the various techniques that the resulting cluster in order to produce a clustering that has lower SSE. Okay, the strategy is to focus on individual clusters since the total SSE is simply the sum of the SSE contributed by each cluster. So here, instead of considering total sum of squared error, that is for all the clusters which we are going to create. For example, if we have 3 number of clusters, instead of considering sum of squared error for all the 3 clusters, we can take one cluster at a time and concentrate only on one SSE for one cluster. Okay, then we can reduce the SSE value. Okay. The two strategies that decrease the total SSE by increasing the number of clusters are the following. First one, split a cluster. So split the cluster, divide the cluster. The cluster with the largest SSE is usually considered. Okay, consider the cluster with the largest value of SSE, but we could also split the cluster with the largest standard deviation. You can use the largest value of sum of squared error, or you can choose the cluster with the largest sum of squared error, or you can choose the cluster which is having largest standard deviation also. Okay. Then introduce a new cluster centroid, and here I forgot to tell you that is a centroid deviation. Sorry, standard deviation. It is for particular attribute. Okay, we have to consider for particular attribute and introduce a new cluster centroid. So instead of considering the previous centroid, use any other centroid. Use other point as a centroid. Often the point that is farthest, that is far away from any cluster center is chosen. Okay, the cluster center, whatever you have taken, the new point, the new centroid which you are going to select, that must be far away from this cluster center. We can easily determine this if we keep track of the SSE contributed by each point. So what we can do, we can keep track of, we can store the values of sum of squared error somewhere. Okay, and we have to check for each point which is contributing, that is which is making the SSE value to increase. Another approach is to choose randomly from all points or from the points with the highest SSE. So this is another approach. We can choose randomly, that is new cluster centroid, randomly as any some point you selected, or you can choose the point with the highest SSE. You can choose the point with the highest standard, sum of squared error. That's why you need to keep track of SSE. Two strategies that decrease the number of clusters while trying to minimize the increase in total SSE. So instead of increasing the number of clusters, can we decrease the number of clusters? We have to check that. That is in case we don't want to increase the number of clusters. Disperse a cluster. This is accomplished by removing the centroid that correspond to the cluster and reassigning the points to other clusters. Okay, what you have to do? So remove the centroid. You consider some centroid that is which is whose total SSE is least. Okay, whose total SSE is least. You select such a point and remove that centroid. Okay, remove that centroid and assign the points to that particular cluster to other clusters. Okay, you are dispersing whatever you have created, that is the cluster which got created, we are dispersing it. We are removing that by adding those points to other clusters. Okay, the points which belongs to that cluster will be added to other cluster. Okay, ideally the cluster that is dispersed should be the one that increases the total SSE the least. Okay, least increase in the total SSC. Such a cluster we have to consider. Okay, least increase in the total SSC, that such a cluster we have to consider and assign the points of that cluster to other clusters. Okay, so it will reduce the number of clusters. Merge two clusters. The clusters with the closest centroid are typically chosen. Okay, so we can merge two clusters. Instead of two clusters, make it as one. Okay, so while merging, what we have to do, we have to select the clusters whose centroids are closer. Okay, whose centroids are closer and merge it. Another better approach is to merge the two clusters that result in the smallest increase in total SSC. Okay, merge two clusters, select two clusters in such a way that which is increasing the total SSC very least or smallest increase in the total SSC. Select such two clusters and merge it. Updating centroids incrementally. This is another issue. Instead of updating cluster centroids after all points have been assigned to a cluster, the centroids can be updated incrementally, that is after each assignment of a point to a cluster. So what is usually done while selecting the centroids? First we'll select the initial clusters, right? We select some initial points to the cluster and that is initial centroid to the cluster, and we select the cluster. Instead of selecting the cluster for all the clusters at a time, what we can do, we can update the cluster centroid after all, that is after each point is added. After each point is considered, update the cluster. Okay, update the cluster. That is the concept of this. This requires either 0 or 2 updates to cluster centered at each step. Whenever you consider one point, so either 0 update required or 2 update required. Why? Because a point either moves to a new cluster. New cluster means obviously the current cluster and the new cluster both will change. So 2 updates. Okay, both will change to 2 updates, or you are not going to change anything. So 0 update. Using an incremental update strategy, it will guarantee that empty clusters are not introduced, not created. Since all clusters start with a single point. Since all clusters start with a single point, so it will guarantee that empty clusters are not created. And if a cluster ever has only one point, if a cluster contains only one point, then that point will always be reassigned to the same cluster. Okay, if we have left with one point, then that will be assigned to the same cluster, so it will not create the empty cluster. Bisecting K-means. This is another algorithm. The bisecting K-means algorithm is a straightforward extension of the basic K-means algorithm that is based on a simple idea. What is that simple idea? That is to obtain K cluster, split the set of all points into 2 clusters. Okay, consider all the points together and split it into 2 clusters and select the one of these clusters to split and so on until K clusters have been produced. Okay, so I hope you are getting. So consider all the points, split it into 2 clusters. Again, in the next iteration, select one cluster among these 2 clusters. Again, split that. Okay, I hope you are getting. Again, in the next iteration, you select one more larger cluster. Again, you split that into 2. Okay, this will continue until K number of clusters have been produced. There are a number of different ways to choose which cluster to split. So we can choose the largest cluster at each step. You can choose the one, the cluster which is having the size is large. The number of points are more in that. We can choose the one with the number of points more, or with the largest SSC. Consider the cluster which is having sum of squared error more and split it, or use a criterion based on both. That is based on size also and based on SSC also. So you can select the cluster which is having more number of points, and you can check its sum of squared error also. If the sum of squared error is also more, then you can split it. So different choices results in different results, obviously. So when you consider only size, the cluster set will be different. When you consider only SSC, the cluster set will be different. When you consider both size and SSC, clusters will be different. So this is the bisecting K-means algorithm. So first step is initialize the list of clusters to contain the cluster consisting of all points. So create one large cluster. Okay, include all the points into the cluster. That is the initial step. Then repeat. Remove a cluster from the list of clusters. Okay, now remove a cluster from a list of cluster. Initially, what happens? You are going to remove the entire set of points and then perform several trial bisection. Bisection means dividing. Trial bisection of the chosen cluster for I is equal to 1 to number of trials. Number of trials usually number of clusters which you are going to create. Bisect the selected cluster using basic K-means algorithm. So divide the cluster using the basic K-means algorithm, that is by selecting the centroid and dividing the points for different clusters. Okay, then end for select the two clusters from the bisection with the lowest total SSC. Okay, after creating the number of clusters, you select the two clusters which is having lowest total sum of squared error. Add these two clusters to the list of clusters. Okay, add these two clusters to the list of clusters until the list of clusters contains K cluster. Again, so this will be repeated after adding these two clusters to the, that is after the ninth step. After the ninth step, once it is added to the list of cluster, again it will remove a cluster from the list of cluster. That is third step. It will go back to the third step and it will remove a cluster from the list of clusters and it will divide it again using the basic K-means algorithm. This will be done until the list of clusters contains K number of clusters. Okay. So this is bisecting K-means on the 4 clusters example. Okay. So this is the iteration 1. If we want to divide it into 4 clusters, so initially you divide it into 2 clusters. Okay. Initially divide it into 2 clusters. So this is one cluster, this is another cluster. Again, choose the one which is having more number of points in the next iteration. In the second iteration, you can notice that. So this is selected and it is divided into 2 clusters. Then in the next iteration, select this. Okay, select this. So in the third iteration, this will be divided into 2 clusters. So total 4 clusters got created here by using bisecting K-means algorithm. K-means and different types of cluster. K-means and its variations have a number of limitations with respect to finding different types of clusters. We have some variations, okay, and it has limitations also. We'll see that what happens with the various diagrams. We'll see that K-means has difficulty detecting the natural clusters when clusters have non-spherical shapes or widely different sizes or densities. So here. With the K-means algorithm, it is very difficult to select the natural clusters. So when the clusters don't have in globular shape, non-spherical shapes. Okay, if the clusters don't have, it is not in the non-spherical, cluster is in the non-spherical shape or cluster not in the spherical shapes, then it is difficult to detect the natural clusters using K-means. And when the clusters are of different size or different densities, then also it is difficult to detect the natural cluster. Okay, this is illustrated by the figures 8.9, 8.10 and 8.11. This is in the next slide. You can notice that. In figure 8.9, this is figure 8.9, that is we have A and B, figure A and figure B. Figure A contains original points and figure B contains 3 K-means cluster. So you can notice that K-means cannot find the 3 natural clusters because one of the cluster is much larger than the other 2 clusters because of the size of the cluster in between. So you can notice in the original point, this is one cluster. Okay, this is one cluster. This is another cluster. You can notice that this is another cluster, and whatever it is remaining in between, this is one more cluster. So it has to divide like this. It has to divide like this, but because of the size of the middle cluster, because of the size of the middle cluster, what happens here? The larger cluster is broken. This larger middle cluster is broken, while one of the smaller cluster is combined with the portion of the larger cluster. The smaller cluster, it is combined with the portion of the largest cluster. So you can notice that also. Okay, so here this is one cluster. After creation, this is one cluster. Then this is another cluster. Okay, after dividing, and this portion of the larger cluster, it is merged with this small cluster. This is because of the size of the middle cluster. So it has the K-means algorithm created cluster like this, but we want the clustering to happen like this. That is whatever I have shown in the shown with the original points, but it has created like this. That is one problem. Another problem is K-means fails to find the three natural clusters because the two smaller clusters are much denser than the larger cluster. Okay, these two clusters are denser. Dense means the points are very closer. Okay, dense means the points are very closer. You can notice that this is one cluster, this is another cluster, and the larger cluster, whatever we have, it is not dense. This is sparse. The bonds in this cluster, it is sparse, right? But in these two cluster, it is dense. So what happens in this? It will, the K-means algorithm will combine these two into one cluster. It will combine these two into one cluster, and it will divide this larger cluster into two. So this is how three clusters got created. Actual cluster was, this is one, this is another second one, and this must be the third one. But what happens here? So because of the density, it has merged these two clusters together, and this larger cluster is split into two clusters. Okay. Then in figure 8.11, K-means find two clusters that makes portion of the two natural clusters, because the shape of the natural cluster is not globular. It is not spherical. Okay. So since it is not spherical, actually this is one point. So these points, this is one cluster. This is one cluster, and this is another cluster. Okay, this is another cluster. But what is happening here? It has created clusters like this. This is one cluster, and the remaining whatever we have, that is one more cluster. Okay, it has created like this. This is because the shape of the natural cluster, it is not spherical, it is not globular. Okay. The difficulty in these three situations is that the K-means objective function is a mismatch for the kind of clusters we are trying to find, since it is minimized by the globular clusters of equal size and density, or by clusters that are well separated. Okay, that is the problem with the K-means algorithm. For K-means algorithm, the cluster, the original points or the clusters which we are going to find, that must be in the form of globular, in the form of global. Okay, round shape. Okay, and it must be of equal size or density. If the density changes, if the size changes, and if the shape changes, then it will not create the clusters properly. These limitations can be overcome in some sense if the user is willing to accept a clustering that breaks the natural clusters into number of subclusters. If the user is willing to divide the clusters into, that is, increase the number of clusters, Okay, instead of creating 3 clusters, create 6 clusters. Instead of creating 4 clusters, you create 8 clusters. If that is the case, then it will create the natural clustering. Okay, so figure 8.12 shows what happens to the 3 previous data set if we find 6 clusters instead of 2 or 3. Okay, so you can notice that this larger cluster is divided into 4 clusters. That is figure A. Okay, figure A, it has created 6 larger clusters, 6 smaller clusters. Okay, this as one cluster, at least these two retained, right? It was mixing with the larger one, right? Now it has retained these two, and this larger cluster, it is divided into 4 clusters. Okay, so total 6 clusters. In this also, these two retained as it is. Even though it is dense, it is not merged. It is divided as it is, and this larger cluster is divided into 4 cluster. Okay. In this also, instead of merging the points from one cluster to another cluster, it has divided naturally, right? So this different shape is divided into 3 clusters. 3 cluster and another shape. This is divided into 3 clusters again. So total 6 clusters. So at least it has not merged the data with or points with other clusters here. Okay. So using the K-means to find clusters that are subclusters of the natural cluster. So it has created subclusters. Instead of merging it into another cluster, it has created subclusters. Strength and weakness of the K-means algorithm. K-means algorithm, it is simple and can be used for wide variety of data types. It is also quite efficient. It is efficient algorithm even though multiple runs are required. Some variants of K-means algorithm, that is, for example, bisecting K-means, are even more efficient and are less susceptible to initialization problems. Okay, even though while initializing the centroids, if you make some mistakes, but bisecting K-means are efficient to find out the natural clusters. K-means is not susceptible for all types of K-means, it is not suitable for all types of data. We have just seen with the example, right? So it cannot handle non-globular clusters, or it cannot handle clusters of different size and densities. We have seen that. Although it can typically find pure subclusters if a large enough number of clusters is specified. So in this case, what we have to do, we have to find out more number of clusters. So subclusters it will form means it will create natural clusters. K-means also has trouble clustering data that contains outliers. Outlier detection and removal can help significantly in such situations. So when we have outliers in the data, we can detect and remove those outliers to find the natural clusters using K-means algorithm. And finally, the K-means is restricted to data for which there is a notion of a center. It is restricted to a data that has notion of a center or centroid. So here this middle point, it is required for the K-means algorithm. Only such data can be used for K-means algorithm. Other kind of data like we have seen that if it is a document data, we have to use cosine values, right? We have seen that in the previous class. So it is restricted to the data which can create the center of the values. Okay, a related technique K-means clustering does not have this restriction, but it is more expensive. That is for the documentation data we use K-means clustering. I told you this in the last class, right? For the document kind of data, we can use K-means clustering. It is not having this restriction. That is, it has to create a centroid or middle point, but it is more expensive when compared to this K-means. Okay, I hope you understood the concept. If you have any doubts, you can ask me.